By the mid-1920s, physics moved fast and pulled in two directions at once. Quantum mechanics had started to explain atoms with surprising accuracy. It treated nature as waves and probabilities, not tiny planets on fixed paths. But electrons did not just sit quietly in atoms. They also raced through space. And at high speeds, Einstein's relativity changed the rules for how energy and time worked. Physicists expected these two ideas to fit together because both described the same world. Instead, they clashed. Quantum equations handled slow electrons well, but they ignored the speed limit of light. Relativity described fast particles well, but it did not speak the language of quantum waves. When scientists tried to combine them, the results often broke something important. The electron stayed at the center of the problem. This mismatch mattered because the electron was not optional. It carried electricity, built chemistry, and shaped every atom. If the basic theory failed for electrons moving fast, the foundation looked cracked. So the challenge became urgent and clear. An equation had to describe an electron as a quantum wave and still obey relativity. Until that happened, the new physics remained incomplete, no matter how many successes it claimed. In 1928, a young English theorist named Paul Dirac tackled the problem head-on. The electron needed a quantum rule that also respected relativity, and the existing attempts either bent the physics or broke the math. Dirac aimed for something cleaner. He searched for an equation that treated space and time properly, yet still behaved like a wave rule for particles. He wanted one framework, not a patchwork. Dirac's move sounded simple, but it was bold. He rebuilt the relativistic energy rule into a new kind of wave equation. To make it work, the electron's wave had to carry extra internal information, not just a single number. Those added pieces acted like built-in switches. Without being inserted by hand, they produced a natural explanation for electron spin, as if the equation already knew the electron came with an intrinsic twist. The payoff arrived fast. When Dirac applied his equation to the hydrogen atom, it did not just give energy levels in a rough way. It captured the subtle splitting of spectral lines known as the fine structure. Experiments had seen those tiny shifts, and the new equation matched them with striking accuracy. A relativistic quantum electron finally behaved as it should. The crack looked sealed, at least on the surface. Dirac's new equation worked almost too well. It described the electron the way it actually behaved, and it fit with relativity without bending the rules. But when physicists solved it, an extra set of answers appeared. The math did not just allow the electron to have certain energies, it also allowed energies below zero. Not a small correction, a whole mirror world of negative energy. At first, that sounded like a mistake you could simply ignore. But the equation did not let anyone do that. The negative energy states came out as cleanly as the positive ones, from the same logic. If the positive solutions stayed, the negative ones stayed too. And they brought a dangerous consequence. An electron in a normal state could, in principle, fall downward forever, dumping energy without limit. That possibility clashed with common sense and with the stability of matter itself. Electrons did not behave like endless waterfalls, yet the equation kept insisting this hidden option existed. Physicists faced a choice that felt impossible. They could patch the theory and break its elegance, or accept that nature had room for negative energy states and then explain why ordinary electrons never plunged into them. By 1929, the negative energy states stopped looking like a small flaw and started looking like a trap. If an electron could fall into ever lower energies, ordinary matter should have collapsed. Dirac answered with a bold rewrite of what empty space meant. He treated those negative levels as already occupied, completely filled. The vacuum in this picture carried an invisible crowd of electrons that could not be seen because nothing had room to drop. That move changed the rules. With every negative energy state filled, a normal electron could not simply tumble down because it would have needed an open slot, and there was none. Stability returned, but at a price. Empty space stopped being truly empty. The only way to notice this hidden structure was to disturb it. If enough energy struck the vacuum, it could lift one of those buried electrons up into a positive energy state. And that left something behind. A single missing electron in that filled sea behaved like a real object, not a bookkeeping trick. It acted like a particle because other electrons in the sea could move to fill the gap, making the whole travel through space as if it had its own motion. The vacuum, once treated as nothing, now carried a new kind of absence that could, in principle, be observed. Dirac's picture now forced a very specific consequence. If every negative energy state stayed filled, the vacuum stayed stable. But if one electron got kicked out by a burst of energy, its absence acted like something new. That hole could not behave like an electron because it was defined by what was missing. It had to respond the opposite way to electric fields. It had to look positively charged. The logic went further. The hole did not carry its own matter. It was a gap in a sea of electrons. So its mass could not be arbitrary. It matched the thing that had been removed. In practice, that meant the hole acted as a particle with the electron's mass, but with the sign of charge reversed. Not heavier, not lighter, equal mass, positive charge. That combination narrowed the options to one. This was the concrete birth of the anti-electron. It was not a loose metaphor, and not a mathematical trick. Dirac's equation and the sea idea demanded a partner to the electron, a twin in mass, an opposite in charge, able to appear when enough energy disturbed the vacuum. But nature had not yet shown it. No one had seen a track for it. Still, the prediction sat there, waiting to be tested. By the early 1930s, the prediction no longer felt like a clever idea on paper. It sounded like a challenge. If an anti-electron existed, it had to show up somewhere, sometime, as a real track in an experiment. But it would not appear in ordinary materials on demand, so physicists looked upward. Cosmic rays, crashing into the atmosphere, delivered natural bursts of extreme energy. Those cosmic particles created showers of fast-moving fragments, and the problem became simple to say and hard to do. Catch the rare moment when something new flew through a detector. The best tool was the cloud chamber. It used a supersaturated vapor that turned a passing charged particle into a visible line of droplets. Add a magnetic field, and the curved track revealed the sign of the charge. Now the hunt intensified because the clue was specific. The track had to bend like a positively charged particle, yet lose energy and scatter like something as light as an electron. Heavy positive particles already existed, and they left different signatures. The cloud chamber, paired with cosmic rays, turned the sky into a particle source and the lab into a sorting test. A single unexpected curve could settle everything. In 1932, the hunt finally narrowed to one person and one kind of evidence, a single curved track in a cloud chamber. Carl Anderson, a young physicist working with cosmic rays, watched charged particles leave visible paths as they crossed the chamber. A magnetic field bent those paths, and the direction of the bend told him the sign of the charge. One track bent the wrong way for an electron. Anderson did not stop at charge. He needed mass because lots of particles carried positive charge. The curve's tightness showed how hard the particle was to push around, and that depended on mass and speed. He compared the track to what an electron should have done under the same conditions. The surprise was not just that it was positive, it behaved like an electron in weight. That combination was the key. Positive charge, but electron-like mass. It matched the strange prediction that had sounded almost like a bookkeeping trick inside a theory. Dirac's anti-electron was supposed to look exactly like an electron, except for its charge. Now the cloud chamber offered a real candidate, written in a single line of vapor, a prediction turned into a particle. Anderson's strange track did not settle anything by itself. One photograph could have been a trick of the setup, or a particle behaving in an unexpected way. So other groups checked the same idea with fresh data and tighter controls. They added stronger magnetic fields to see the curve more clearly, and they placed dense plates in the path to measure how the particle lost energy. The question became simple. Did the numbers stay consistent? They did. The track curved the way a positive charge had to curve, and the amount of bending matched a particle with the electron's mass, not a heavy proton. When the particle passed through a metal plate, it slowed down exactly as a light particle should, and its path still made sense on both sides of the plate. That removed the easy escape routes. This was not a misread proton, it was something new. Once the measurements held up, the interpretation snapped into place. The particle matched the anti-electron predicted by Dirac's theory, so it needed a clear name. Physicists called it the positron, and that name carried a larger consequence than any single lab result. A mirror version of matter existed, not as math or a story, but as a real particle that left real tracks and followed real rules. After the positron stopped being a one-off surprise, the next question became simple and brutal. Did it behave the way the theory demanded? In the years that followed, researchers pushed to see it appear on command, not just by chance in cosmic rays. They fired energetic gamma rays into heavy materials and looked for a telltale split. One photon went in. Two tracks came out, curving opposite ways. Pair production had left fingerprints. That result carried a hard message. Energy had turned into mass, and it had done it symmetrically. An electron and its mirror partner born together. Measurements tightened. The two particles matched in mass, but their charges balanced perfectly. Then the reverse process appeared just as clearly. When a positron met an electron, both tracks ended abruptly, and new radiation carried the energy away. Matter and antimatter had not just existed, they had interacted exactly as expected. As experiments improved, the radiation from those disappearances showed a precise pattern. The energy came out in two gamma rays with a fixed amount, shot in opposite directions to conserve momentum. It was not a vague flash, it was a signature. With pair production and annihilation now repeatable, the positron stopped being a curiosity and became a working piece of physics. Dirac's equation no longer looked like clever math, it looked like a map of real events. By today, antimatter no longer belonged only to bold equations and rare cosmic ray tracks. It got made on purpose. Accelerators routinely produced positrons, then steered and stored them long enough to test their behavior with care. The idea that had once sounded like a loophole in mathematics turned into a controlled recipe. Antimatter became something engineers could count, detect, and use, not just something physicists argued about. It even entered medicine. In PET imaging, hospitals used short-lived isotopes that released positrons inside the body. Each positron quickly met an electron, and the pair annihilated into bursts of gamma rays that detectors caught outside the patient. Computers then rebuilt a map of where those annihilations happened, revealing active tissue and tumours. A prediction born from a crack in theory ended up guiding real diagnoses and treatment decisions. And the equation itself kept growing in importance. Dirac's work became a starting point for quantum field theory. The modern framework that treated particles and antiparticles as two sides of the same deeper rules. What had been a desperate attempt to make the electron obey both quantum mechanics and relativity ended up reshaping how physics described the vacuum, forces, and creation of matter. The old crack did not get patched, it got turned into a doorway.